everybody. So this is a Wednesday morning session. So it's nice to have all of you. I think some people are a bit late, but I mean, I hope they're going soon. So today we have the keynote speaker Jacopo Iollo coming from INRIA Grenoble in France. And you're going to talk about diffusion-based Bayesian experimental design. The floor is yours.
Thank you. Thank you for your introduction and thank you for the invitation to present my work. So my name is Jacopo. Up until last month, I was a PhD student at INRIA Grenoble, and I just defended. So I'm very excited to be here in Cambridge to give a presentation as a doctor now. So I'll be talking today about Bayesian experimental design and how can we essentially leverage diffusion models to extend the scope to which we can apply essentially Bayesian experimental design. So as a light overview of my talk, so Bayesian experimental design in one sentence would be about optimizing the data acquisition process, meaning that you have an experiment variable xi, an outcome of the experiment y, and you want to optimize or choose the best experiment xi in order to give you the most informative data as possible. And all of this somehow relies on inference, meaning that we are somehow trying to predict the impact of an experiment. When we want to choose an experiment, we are trying to predict the impact of an experiment before making the experiment. Also, if you work in the sequential context, you can use inference to somehow update your prior and integrate the new data. And also the goal of the overall procedure of Bayesian experimental design is usually to get an estimate of the parameter theta. So this will rely on inference. And so one of the constraints that come with this is that it somehow relies on closed form prior to run Bayesian computation. And this somehow limits the possible application of Bayesian experimental design. And so today, with this work, we'll try to move away from this constraint by leveraging diffusion models, essentially. And so I like to start always presenting Bayesian experimental design with the simple toy model of source example. That would be very useful to illustrate our method. So you have an observed data that represents the intensity of a signal. Position of a source theta that you're trying to recover, and the experiment is where in the domain you query, you measure this intensity. And with this model, we can already have a good intuition about what good or poor measurement are. So poor measurement would be measurements that are taken far away from the position of the sources, okay? And so you will gain very little information because most of the value that we'll be measuring is close to zero. On the other hand, if you have good measurement, on the right-hand side here, those will be taken close to the true position of the sources, will have high intensity, and will tell you a lot about where the position of the source is. And so the situation that we want to optimize for is to be in the situation upper right. And so in order to characterize that situation, we'll be working in the typical Bayesian framework. So with the prior that represents the knowledge before the measurement, a likelihood that measures the data compatibility with your parameter, and a Bayes theorem essentially allows you to write down the updated knowledge after the measurement as the posterior. And then the main idea of experimental design is to say, okay, depending of where I query, what experiment do I run, I will have a different shape of the posterior, okay? And the situation that we want to be in is to be in this case where the posterior is really concentrated in some part of the domain, meaning that you're really sure about the prediction of our parameter. And so in order to characterize that, we will work with the entropy of the distribution. So if we start with the prior that has high entropy, so here in blue, and we take a poor uninformative measurement, the posterior will change very little from the prior, and it will still have a high entropy. On the other hand, if we take good and informative measurements, the posterior will be more concentrated in some part of the domain. So it will have low entropy, meaning that we're more sure about the prediction of our parameter. And so this is the situation that we want to be in somehow, so this maximal reduction in uncertainty. And so as we don't know the outcome of the experiment before running the experiment, The typical idea is to define the expected information gain is to say, okay, I'm going to average over all possible outcome. And so this will define the expected information gain, and Bayesian experimental design goal is then to find the experiment that maximizes this quantity. And so we want to run an optimization to find this experiment that is expected to reduce the uncertainty the most. And we will work in a setting where everything is continuous and differentiable and try to derive gradients of that quantity. So one of the main issue with this expression is that there is the posterior in there. And so the posterior is first expensive to compute, and then it can also not be clear how to differentiate it with respect to psi. So in the literature, lower bound have been proposed as a proxy for maximizing the expected information gain. So the idea is to work with this lower bound where everything is computable, and to run a stochastic optimization to find the optimal design. Okay. But today, so we'll be working in a setting where the prior is not available. And so if the prior is not available, you have a bit more complexity in deriving this gradient. And so in what setting can we have no closed form prior? So as soon as you work with images, typically it will be very hard to set up a closed form prior. So for example, in this somehow tau example where we want to reconstruct the image by observing just a little red square of the image. And the design is that we can choose where we put this little red square on the image, so we can move it around the image, okay? And so the parameter space here is the matrix of all the pixels of the image. And so in this scenario, it's already not clear how I would choose a closed form prior for the MNIST dataset. And then if we move also to like more real life example, for example, MRI acquisition. So in MRI acquisition, you go inside an MRI machine that emits a magnetic field from which you can measure some Fourier frequencies that represent this K space. And then if you have all the frequencies, you can apply the inverse Fourier transform to recover the part of the human body that you care about. So here, the brain. And here, it's even more difficult to think of a closed form prior that you would use for this use case. Okay. And so today I'll be presenting this work, CODIF, that tries to extend Bayesian experimental design to higher dimensional example, for example, images by leveraging diffusion models. And I will also briefly talk about Sharingan, for which my PhD classmate has a poster, where we try to apply this algorithm to improve efficiency of an MRI acquisition process. Okay, so let me start with the first contribution. And so up to now, in Bayesian experimental design, I've mostly been working in the setting of model-based, meaning that we have a closed form prior that we can easily sample from. And we need to run computation to sample from, to do inference and sample from the posterior. And so the database sampling is a setting a bit different. You don't have access to a simple closed form prior. You have access to a dataset of this prior. And from this dataset, you can learn with a neural network some functional, for example, the score function, with which you can run a denoising process with the diffusion model in order to generate new samples. Okay, so we still have somehow access to a prior, but in order to sample from a prior, we now need to run computation. And we can still sample from a posterior by running computation. And so if you look at the gradient expression of the expected information gain, you see that now these there are now two distributions for which we don't have access to. And on top of that, they are here evaluated as densities, okay? But what we are better at with diffusion models is generating samples, so sampling. And so we try to derive a gradient expression for the expected information gain using the following ingredients. So first of all, the knowledge of the forward model. So in this case, we know that the forward model just select a part of the image. Then we also know how to generate samples from the joint distribution, meaning sample from a prior of MNIST generate new sample, and then applying the diffusion models to generate the measurement corresponding to these samples. We also know how to generate conditional samples by diffusion models. So if I observe this little square of the image here, I know how to generate samples that are consistent with this measurement. Yeah. And so it turns out that it's possible to slightly rewrite the gradient expression to have both those densities evaluated by sampling. Meaning that if I were to estimate this gradient by Monte Carlo, we only need samples from this true distribution and not their densities, okay? But we still have a problem of nested estimation because applying a straightforward Monte Carlo estimator here would require to run n separate inferences for each different posterior on yi here because of the outer sum. And so this is, as there are like n of them, it's quite expensive and not really scalable to real problems. And so the idea is to use, you can use importance sampling essentially to move the dependence of yi inside the inner expectation, okay? And so the choice of a proposal of importance sampling distribution is constrained by the fact that you want the importance sampling to have low variance, so to be somehow as precise as possible. And so a typical metric that is used in that case is to reduce the distance from Q to P in terms of the chiral divergence. But here we don't have just one importance sampling, we have actually n of them because of the outer sum here. And so you can use as a metric this weighted chiral divergence instead, but try to take the best possible importance sampling distribution in a mean sense over all your possible yi. And it turns out that minimizing this distribution constrains Q to have this geometric mean of contribution of yi, yn that we name the pooled posterior because it essentially tries to average or to pool all these different y contribution. And there is a really nice interpretation for what it represents in the case of the sources example. So if you look at this example, and when you sample the yi, given that your measurement location is this orange dot on the image, as in the current state of the prior, most of the sample yi, most of the sample theta I are far away from my measurement location. Most of the yi will be close to 0. So very low intensity. And what this says is essentially that given my current state of the prior, the expected measurement that I'm probably going to make is the expected value that I'm probably going to retrieve is 0. And so what the pool posterior is trying to take into account here is the outcome of this experiment. So if I measure a value of 0, it means that the source is probably not around my measurement location. And so it is essentially moving all the particles far away from my measurement location. And you can see the Xi optimization path in blue here. And so in this case of the sources, this also illustrates the contrastive behavior of the procedure, where here we are trying essentially to make the pool posterior as different as possible from the prior. So here to make somehow the biggest hole as possible in the prior. Okay. And now, so to resume, given samples from these two distributions, we have a way to estimate our gradient that we can write simply as a function gamma. The question is now how to generate these samples that we need in order to estimate this gradient. And in order to do that, we'll be using particle methods and define an operator sigma such that the iteration of sigma on some particle that start randomly distributed, after s iteration of sigma, you will get particles that are distributed around your desired distribution. So you can think of sigma as your favorite somehow MCMC kernel. And so in the case of a pool posterior, it's very nice because of the form of a pool posterior. You can essentially use any score-based sampler that you have used on the normal posterior. You can use it on the pool posterior because the score of a pool posterior writes down as the sum, as this weighted sum of individual scores. Okay. In the case of images and so diffusion models, similarly, if you want to generate conditional samples, what you need to do is to run a conditional backward process. And so this was presented to us on Monday's tutorial, but essentially the issue here is that this conditional score decomposes in two parts. One part that you know because it's the neural networks that you have learned, and one part that you don't know and you need somehow to approximate. And so there has been like really a lot of work in how to do this approximation recently. But the typical template that can be used is to write down an error vector that measures the discrepancy between your measurement y and the predicted measurement somehow based on the current noise state at time t. And then a projection matrix that projects from the space of y this back to the space of to the x space. And you can also add, you will usually need to add also a scaling factor that adjusts the guidance in order to have convergence of your samples, okay? And so now, if I resume a bit everything, we know how to generate this sample by applying S step of this sampling operator. But as these, so essentially these distributions depend on xi, that is the outer parameter that we are trying to optimize. And so the question is, as this distribution depend on xi, do we need to start the S sampling iteration from start each time we move xi with a gradient step, essentially? And so we have somehow in a bi-level optimization framework with an inner sampling loop that depends on an outer parameter xi. And so in the context of diffusion models, this was studied recently by this recent paper and proposed to do everything together. So to move from a nested loop to a single loop. And so you will be letting all quantities evolve together. The xi of the gradient optimization and the diffusion on your parameters. And the intuition is that you don't always need to have samples, perfect samples to run the stochastic optimization on. And when xi will stabilize, the samples of the diffusion will stabilize with it. And so this allows us to move from a nested loop to a single loop, and it is a big efficiency gain. And so this is obviously very similar of a lot of work that has been proposed in the joint optimization of the UAG, where we let all quantities evolve together. And so to illustrate this method on the source localization problem, we ran experiment, and as you can see, little by little, you can see the particle approximation that converges to the true position of the sources. Then we also benchmarked it quantitatively in terms of information gain first, with respect to recent methods from the literature. So there are here two greedy methods, so VPC and a previous method from our group that uses sequential Monte Carlo and tampering for a precise posterior estimation. And this was benchmarked at low particle counts. So low is somehow around 400 samples. because essentially for 400 samples is typically what you can afford to have in terms of images on the GPU. With more particles, you will run out of memory. And so the coding algorithm here is the orange curve. And what's interesting to note here is that even if it's a greedy method, it still outperforms non-greedy method, for example, reinforcement learning, because I think that reinforcement learning have no posterior estimation. And in cases, in example like the sources, there seems that the posterior carries more information that planning several steps ahead. And then we also measured the quality of the posterior approximation, essentially. And the CODIF algorithm, still with the low particle count, converges very well to the ground truth. And then, so we also tried on the main example that was this reconstruction, this image reconstruction of on MNIST. So again, here we have a little red square that you can move on the image to select what part of the image you want to observe. And the design question is, what part of the image should I observe first? And so we'll be seeing on top the high weight samples and bottom the low weight samples from the distribution. And little by little, we managed to recover the ground truth image. And then we compared this with the random measurement of the image. And so if you take a square that is not too big and you do random measurement on the image, most of the time you will not capture enough information. So here you can see that with random measurement, you don't capture enough information to properly infer here on the bottom your truth image. Whereas if you optimize your measurement, well, you can almost certainly retrieve your ground truth image. And so this was also a measure in terms of this metric SSEM with respect to random. And so as conclusion of the CODIF algorithm, it's a new gradient-based Bayesian experimental design approach that allows to extend this setting to higher dimensional examples like images that are not captured by the closed-form prior. And simple limitation is obviously that it's still a greedy approach, and we need an explicit likelihood requirement because we need the knowledge of the forward model. And also because of the conditioning methods used for diffusion, this for now focuses on linear forward models. So this is simple extensions and future direction that we can think of. And now I want to show how we applied somehow this framework to this INRIA acquisition problem. That was so a collaboration with my PhD classmate Geoffroy, and so our supervisor Florence. And so in the INRIA acquisition, so you measure these Fourier frequencies. But the problem is that the full acquisition of a K-space is time-consuming. So it's both expensive for the hospital and quite uncomfortable for the patient. So a lot of research has been made about how to select the most important frequencies. So you can define a mask that is parameterized by some Xi. And then depending on the Xi that you choose, it will select different frequencies in the domain. And so the goal is to optimize this subsampling pattern to choose these Fourier frequencies. But once you have these subsampled Fourier frequencies, you can no longer just apply the inverse Fourier transform because you lack a lot of a spectrum. So the goal is to leverage diffusion models to complete essentially this missing information. And so you can apply the CODIF algorithm to have, so diffusion complete the missing information about the K-space and Bayesian experimental design to find the best subsampling pattern. And so iteratively, this will, as you can see, this will select the best frequencies, okay? make an estimation based on frequencies of the reference image, and by iterating this procedure little by little, your prediction of a reference image will get closer and closer to the ground truth image. And so very quickly, there is a lot to gain by doing experimental design at what we call high acceleration, so a setting in which you measure a few frequencies on the domain, but very little to gain at low acceleration. Low acceleration is the setting which you're taking as measurement a big part of the K space, because if you're measuring a high percentage of the K space, it doesn't matter much if you're taking a random experiment or optimizing them. Okay. And next, I wanted to talk about this Python package that we developed in order to run our research for an efficient research in diffusion model. And this again was done with Geoffroy. And so diffusion models, as we saw on Monday, typically represent, you start from an image from a data set, and you can add noise little by little until you get to a completely noised image, okay? And you can kind of do it, for example, like mixtures. You can start for a mixture, add noise little by little until you converge to a unit Gaussian. And then, in order to generate samples from your base distribution, so a distribution of images that you care about, you can go backward in time. And so in the case of a mixture, you can go back from the unit Gaussian back to the mixture. And in order to run this backward diffusion, you need to learn the score function, typically with a neural network. And so if you've worked with diffusions, you probably know that there is plenty of methods in the literature on how to do each part of this process. And so I like to think of this as somehow an experimental science. So there is a high need to evaluate how much an idea actually contributes to the performance in your use case somehow. And so with Diffuse, the goal was to have a practical and efficient software to test essentially every of these different methods. And so the approach that we took is to essentially modularize computation in exchangeable blocks. So each block kind of sits on top of a previous one. So from start, you can start with a noiser that will essentially define the time discretization and how noise is added to your image. On top of that, you can define a denoiser that will define how you generate new data, and also how to do like a single-step discretization, from which you can use it so to this conditional sampling block that will allow you to run to generate conditional images based on your observation. And on top of all of that sits our CODIF algorithm. Okay. And for each of these blocks, the main idea is that you can choose from each of these previous methods from the literature. And so in code, this takes place in this really, I think, neat way. So for example, we can start by defining this noiser. So for example, if you're taking a variance-preserving formulation, it will add noise in this way with essentially a Gaussian convolution with noise. Then you can define a timer that will choose how you discretize your time domain. And the integrator, for example, you can use the DDM integrator that sets up how you would run a single denoising step. And with the integrator, you can set up this conditional approximation. So one of the first method that was proposed was this denoising posterior sampling, where essentially the error vector is approximated with a 3D estimator from the noise at time t. Then with that, you can generate conditional sample by just calling this method. And what's really important for us is that you can also define a single step of denoiser in time. And this is fundamental for the CODIF algorithm. And again, what's really nice is that you can choose for each of these different blocks what you want to use and just run it in the same way for all the different methods. Okay. And so I wanted to illustrate this on some of this mixture example. The mixture example is really nice because you have all your quantities available in closed form, so you can essentially see if your algorithm are correct, at least on mixtures. Okay. So you can see here on top, you start from a unit Gaussian, and then you see the time evolution until you go back to the original mixture. And so in blue is the theoretical distribution at empty, and in red is the samples that we have generated with our diffusion method. Okay. And to illustrate the different choice, so you can, let's start with the time discretization. If you take times that is well spaced in the time domain like here, and an Euler-Marioma integrator, you will kind of get this stochastic pattern. And then if you choose your time to be like more focused toward the ends of the denoising, with respect to the same number of steps, you will spend more denoising step in the setting in which your modes of your mixture are well separated. And this allows essentially to choose where you want to put your computational effort. Okay. Then also you have all different sort of integrator. For example, deterministic integrator. So for this DDM integrator where everything is no longer stochastic but more deterministic. But you can also choose to have something in between. So with a part that is this churn integrator, with a part that is stochastic, and a part that is deterministic. And so for our Bayesian experimental design framework, this is the main loop, the main optimization loop of this algorithm. And we have so two diffusion steps, one for the pool posterior and one for the prior, essentially. And so this package essentially allows us to choose the timer that we would want, the integrator that works best for the use case, and run the conditioning method, and you can then run the algorithm in the same way, whatever the choice of this parameter you take. Okay. And so, as a recap for our work, we took this sampling as optimization approach to guide the optimization with inference, and use and leverage diffusion model to extend Bayesian experimental design to these higher dimensional examples, for example, images. Then we applied Bayesian experimental design to accelerate medical images acquisition with the algorithm that we just developed. And finally, we proposed diffusion, so a tool to kind of help you set up this algorithm for your use case. And so as future direction, I think there is a high need to stabilize somehow this joint optimization. And I see two main directions that are interesting. So first of all, look into other proposal distribution other than the pool distribution that might have some better qualities somehow. And also, there's been a lot of recent work on these one-step models in diffusion, so that essentially allows you to denoise in one step until you go to your data space at time t0. And so these are with consistency model, shortcut model, also distillation. And it would be very interesting to see how we could leverage these methods to our use case of Bayesian experimental design. And also another very interesting direction is this implicit setting that will be very useful, for example, for anomaly detection in MRI. So in MRI, you know the forward model F, you want to go from the image space to the measurement space, the CAS space here. But if you're working no longer with images of your brain, but you care about some anomaly detection in your brain, there is no explicit forward model here. And so the implicit setting would be very useful to kind of scale up to this kind of setting. Okay. And so to finish, I want to thank so my supervisor Florence for supervising me for these past 3 years, and my classmate Geoffroy for this recent work that we did together. So this is all for me. I will take any questions if you have any.
So we have plenty of time for questions. 23 minutes for questions, so you are more than welcome.
Yes.
This diffuse model is intended or it was designed to test how like this.
Sorry,
Sorry, the diffuse module.
Yeah.
Python, is it designed for testing out different methodologies in some way, or for like doing a high performance of sampling?
So we try to have the best of both worlds, essentially. It's implemented in JAX, so it's somehow really quick by nature. And then in our work, we see typically good performance with respect to other modules that don't have the same kind of possible expressiveness somehow.
I was wondering because if you want to sample like in parallel the different samples of the trajectories of this.
So it works naively on GPUs, and you and you can scale up to like hundreds of samples on one single GPU. For example, for the images, we have 400 total samples when we run our optimization.
Well, did you benchmark that with respect to another?
No, but it's still very much a work in progress. It's very recent, and we plan to benchmark it with respect to other packages or that are made before. Yes.
You mentioned not in the late outlook, but in outlook in the middle, you were saying that you want to extend also to nonlinear inverse problems.
Yes.
Can you mention a bit the main challenges and maybe the way you could address them?
Yeah. So it's so for nonlinear inverse problem, it's the problem is how to condition this diffusion model, essentially. I mean, there's this problem, and also one of the other problem is that we're working with sequential setting, okay? And with sequential setting, when it's linear, you can essentially stack the data together. If you have something that's non-linear, you cannot superpose the data, and so you need a way also to evaluate the score more efficiently if you're in this kind of stall data setting. And so, yeah, first you will need to see somehow how to run your inference if you have several data points and are in this tall data setting. And then for just the conditioning part of the diffusion models, there have been recent work that tries to do that. And one direction that they take is to put a nested a nested somehow inference in the problem. So so if I go back to the main problem, Okay, so you are running a conditional backward process to sample conditionally, and there is this term that you need to approximate. And one possible direction that people have been taking is to running somehow an inference to approximate this term as well. So now you have two loops. But in the case of experimental design, we already have an outer loop. So we'll have 3 inner loops. So that's not really something you can just apply as it is.
Thank you for the talk. So I'm also thinking, I don't usually start reading about experimental design, so this may be a silly thing. But if you have a dynamic problem, so it's like yt is f of xt and theta, and you're looking for theta. It's an inverse problem with some measurements which have a sequential importance. So you can show. So will it be possible to do this in that setting? Because this is all in the context of images where everything is static.
Yes.
And it's like
Yeah, but what would the diffusion model be doing then is what...
there is still a design because the Y's would, for example,
Yeah.
work in tsunamis a bit. So you need to place this sensors where it measures the wave heights at certain locations. Of course, it will depend on the source of tsunami,
But so your parameter is evolving with time. So theta is evolving with time as well.
T is real time.
So it's not fixed in time, theta.
Here it is a pseudo time.
Sorry?
Here it was pseudo time.
I mean, so here it's evolving in time, but the parameter that we care about at the end of the day, it's fixed in time.
Correct. So parameter is still fixed, but the measurements move in time. And the state also evolves. So in imaging is a static inverse problem, and I'm talking about a dynamic inverse problem.
Yeah.
Is it possible to?
Yeah, I guess for me it's not clear if it's this dynamic inverse problem and your parameter that you care about depends on time.
The parameter doesn't depend.
The parameter doesn't depend on time. I mean, yeah, so if you can learn a diffusion model that estimate your parameter, then I guess the problem is how to condition with respect to y that evolves in time. Yeah, that's not something I've thought of really, but maybe there is work in literature on how to do that. But yeah.
I would like to come back to the NRI example. I know there will be a poster, right?
Yeah.
Can you say a little bit more? So, a bit more about what you are doing exactly, how you use your diffusion process. So, is it really to do experimental design and define a selection of points? Okay, can you?
Yeah. So
you were a bit fast.
Yeah. So essentially, you can parameterize this mask with the design parameter xi, and this design parameter will tell. So, for example, here you have two kind of different masks. So on the left here we have the radial mask, and here we have the spiral mask. And depending on the xi that you choose, you can have a spiral that looks like this, or look like this in the end. Okay, and it's the same with the radial. You can choose the angles and the line length, for example. And these are actually the parameters that you will be running your stochastic optimization on. So this design parameter that will define this mask. Yeah, so for me it's not really satisfactory, this setting, because one of the things that you cannot really control, for example, in these two masks, you can see here on the right, you are selecting way more pixels, and here way less. So it's not really at equal budget for now.
Yeah, but about this assumption, so you are running the experimental design for a given image, or this is something that you are going to do systematically for different patient?
No, yet it's really adaptive.
So it's real it's adaptive for
Yeah.
a given patient and a given exam,
Yeah.
right?
So it's adaptive in a sense. So if this is the ground truth image, and you start with no knowledge of this ground truth image, you will start by selecting this, and then you will make by selecting this, you also make an estimate of your current knowledge of what your parameter is, and based on your current knowledge, then you will select the best possible design. And so if you have a different knowledge here you will have a different kind of mask.
Yeah, and in terms of practically when you are doing have you tried in a paper? How much time does it take? Is it competitive compared to the time of the usual exam where you don't do the experimental design?
So is it competitive in computation time or in?
Yeah.
So
is it realistic to use it?
So I think you can always optimize if you can always more optimize the code, but already is not too time expensive. So just one running step, it takes I think 10 or 20 seconds depending on the number of steps and the number of particles that you use, but on a high-end GPU. So that's the cost.
Very interesting.
Yeah.
You have other questions? Yes.
Actually, quick follow-up question here. So the machine allows you to technically quickly reset your sampling pattern.
So this is also like I think a really interesting thing that you need to care about in this setting when you're this mask. It's not clear if they correspond to physical easiness of acquisition of the machine, and so I think there is a lot of work to do. So in this MRI example specifically, in how to design a mask that is efficient to capture for the machine, and also budget constant along when you optimize Xi.
Another quick question on slide 70. 70 or
70.
I think you had a training loop, and do I understand correctly that the prior is trained not offline beforehand, but as part of the whole loop? Was that what you were saying?
No, we train the prior beforehand, so typical diffusion models. And then, so we learn the score function. And then during the inference, the score function used in the same score function is used in these two steps. Because for the pool posterior, you can reconstruct its score function from the score function of an individual.
Okay. And what was the P and what was the Q again?
The P is the noised probability distribution at time t.
Again.
So here, so here just with this algorithm, it's maybe not clear. So t here is the number of optimization step that you're running. But as in the loop, we let everything evolve together. For the data of the images, t represents the noise distribution at time t. And so when you get to the end, you should get completely the noise distribution. And so this actually there is a problem because you can if you want to set a couple of thousand optimization steps, you will with this definition you have a couple of thousand diffusion steps as well. But one simple thing that you can do if you want less diffusion step, if you want, I don't know, 100 diffusion step, you can stack 10 diffusions after each other, so you will get a total of 1,000 steps.
So currently you're saying the number of design decisions and the number of diffusion steps here in this algorithm is coupled, but you could just...
Yes. So in practice, it's decoupled because you will... you want to go quite fast on the diffusion because you get obviously better estimates of everything when it's close to when it's completely denoised. So you want few diffusion steps, and that's the goal of distillation, etc. but you may want to have a lot of stochastic gradient step on your parameter xi, because it takes more time to converge. And so in practice, you somehow need to stack these things. Yeah.
First, congratulations on the very neat presentation. And,
thank you.
Very, very good work. And also the software is an important part in case we use it. So the question is about the registration. So here it seems that in your MNIST example and also in the generated sample for MRI, everything is well aligned. Now imagine that one of your MNIST numbers is rotated.
Yeah.
Is your method accounting for that?
So we didn't test that explicitly, but so something that comes on the top of my mind is that usually the training data, when you train, you put a random transformation of your images in order to augment the dataset. And those transformations typically are rotations, for example. So
okay, but that's a technique that data augmentation that can make your sample very, very large, right?
Yeah.
So, have you thought of other techniques to account for this?
No, that's not really something we have explored. But do you have in mind like a practical setting where this might be arise, or in the MRI in this case?
It's kind of an open research track, I guess.
Yeah. Okay. Okay.
But there are many ways that you can do that, right? But in the context of diffusions and Bayesian experimental design, I don't know if this has been tackled suitably. I'm just interested in the topic.
Yes. Yeah, so you essentially need some equivariance somehow in the condition. Yeah, I don't know.
In the active MRI acquisition,
Can you just speak louder?
sorry. In the active MRI acquisition, you're using a first random measurement, and but you will do like the experimental design as well,
You
right?
say a first random measurement?
Over the slide 58.
What numbers are?
58.
58.
50. 58. Or the active MRI acquisition, again, in the scheme of the algorithm. There, yeah. You initialize with a random measurement, right?
No, the first one is also optimized.
It's also optimized.
Yeah.
Why is it like the first line? The first line of the algorithm says like it's initialized with a random measurement.
Yeah, so I mean, you initialized the optimization with a random measurement, but then you run the optimization to select the actual first measurement.
Okay.
So the initialization of the optimization is no. It's you initialize the optimization randomly, and then we optimize for.
Okay. Because I guess that it's a different process. Like the first measurement that you choose, and the rest of them for a linear inverse problem.
Yeah. So and typically this is also where you see that the optimization is not really stable, because in the best world, because we don't have, when you do the first measurement, you don't have any previous data. So you kind of like what the optimal measurement in that setting should be the same, whatever the reference image is. Okay. But here, depending on how you initialize, you always get something a bit different. So it's because the optimization is not that stable, essentially.
Thank you.
Just a quick comment on that. I mean, it could also be that everything works fine, but
Yeah.
not just multiple equally good first measurements, and then you just converge to one of the many good ones.
Yeah. Yeah, it's not clear, and but it's also why, because I think that. But I mean, this could be true, but when you're taking few measurements, is also the part where you could gain the most for the MRI. So yeah, I'm not really like this formulation for MRI is not really satisfactory to me because if you want a very high precise image, you need to capture a lot of the car space. And in that setting, if you capture a lot of car space, it doesn't matter much if you're optimizing or not.
Okay, so thank you very much for this.